Okay, very good. So it's a pleasure to introduce today's speaker, Daine Danielson. Daine got his PhD at the University of Chicago not that long ago, working with Bob Wall there. And now he's a postdoctoral researcher at MIT and University of Harvard. So I actually met personally Daine a couple of times at a very interesting small workshop in some remote village in the French Alps. So there we had plenty of really interesting physics discussions and more general discussions. I also had the chance to see that he's also a great pianist. So we had also the pleasure of enjoying his performances. And yeah, so Daine has made very nice contributions to the problem of gravitational mediated entanglement and the discussions there, how to interpret the implications, giving some very nice general arguments, covariant and different perspectives. And he's also made very important contributions to a related topic, which is decoherence induced by soft graviton emission, especially in non-trivial space-time backgrounds like black hole spacetimes. So we are really happy to have you here in this seminar series and look forward to your talk. So Daine, the floor is yours.
Well, thank you very much, Albert. That's a very kind introduction. Um, and thanks for having me here. So yeah, I'm just going to tell you about some recent work that I've been doing with Gautam Sadaschandran at Princeton, uh, related to the decoherence that arises outside of black holes and in the presence of a cosmological horizon. Um, but reanalyzing that phenomenon, which I'll review for you from a quantum information theoretic perspective, and trying to understand the underlying basic principles at play um, in the decoherence outside of black holes, et cetera. So I figure this would be an appropriate venue to discuss this. And as I said to Albert, this is work that will be hopefully on the archive within a week or so, but so you'll get a preview here. Um, okay, so I'm going to begin with a thought experiment. Um, and in this thought experiment, I'm going to begin with an experimentalist, Alice, in the space-time of a cold, dead star. So I just want it to be cold and dead so that I don't need to worry about the internal degrees of freedom too much. They're all frozen out. It's just a cold, dead star space-time. And Alice, and you could think of this big gray patch on the right as being the world volume of this cold, dead star in the space-time diagram that is the whole slide. And outside the star, our friend Alice has, in the distant past, used a Stern-Gerlach apparatus to make a spatial superposition of a massive body. And so you can see the superposition coming in from the past. And later, as she enters the causal diamond indicated with the dashed lines, she's going to attempt an interference experiment and look for signs of any decoherence that may have arisen between the branches of her superposition. So, kind of as a cartoon, I've put a kind of interference pattern or a particle-like lump as the two possible outcomes. Of course, in practice, she might do a spin measurement of some kind to check for signs of coherent interference versus decoherence of her particle. And so if she performs her experiment adiabatically, so she does everything very slowly, she can minimize the amount of radiation that she emits. And we're going to assume that she's a great experimentalist. So and she's got all the backgrounds are completely under control. The only source of decoherence she really needs to be worried about is she's got to accelerate her particle uh, uh, in order to perform this experiment at all. And just to bring the branches of superposition back together, her particle needs to accelerate. But as long as she accelerates it sufficiently slowly, so she does the experiment adiabatically, then she should be able to minimize the amount of radiation that she emits due to this experiment, gravitational radiation in this case. And as long as she minimizes the amount of radiation that she emits to ultimately to null infinity, we're imagining we're in an asymptotically flat space-time, and radiation will go off to null infinity, then she can maintain coherence to an arbitrary degree as long as she does things carefully enough. So you could ask a very similar question. From the point of view of Alice, it seems like a very similar question, which is, what if Alice was going to do the same exact experiment where the local metric in her lab is precisely the same, but I've replaced the neutron star, the cold dead star, with a black hole of the same mass. Okay, so Alice is sufficiently far away that to her it just looks like exterior Schwarzschild space-time, but really, now there's really an event horizon, and there's really a black hole. So then what happens? We'll have Alice follow the same protocol that she did before. She's going to do things adiabatically to try to minimize decoherence. But now there's one big difference, which is a global difference that this space-time has relative to the cold dead star, which is now there's a big interior space-time region corresponding to the interior of the black hole. And a hypothetical observer, Bob, could be living in the interior. And of course, I'd like the black hole to be sufficiently large, that so he doesn't die instantly. Ultimately his fate is sealed, but we'll give him plenty of time in the interior by allowing the mass to be sufficiently large. Then he can see the superposed Newtonian field sourced by Alice's superposition outside. And he could, for example, release a test particle from a trap in the interior. And that test particle would evolve into a superposition of trajectories just due to the superposed Newtonian field. So this produces an apparent paradox, because our intuition from the cold dead star was telling us that Alice should be able to absolutely minimize her degree of decoherence. But in this case, Bob is able to perform a Witch path measurement on Alice by releasing a particle and becoming entangled with the Newtonian field. So it would seem that there's a conflict between causality and complementarity, because, as I said, Alice is going to perform a test to see whether or not her particle is coherent. So she can learn the degree of decoherence that she suffered. But if the degree of decoherence she suffered depends in any way on what Bob has done, whether or not he performed a measurement, then there would obviously be a causality paradox, because Bob would be able to affect the outcome of her interference experiment from behind an event horizon. So this is a paradoxical situation that we noticed a few years ago. And when you think about it for a little while, you realize there is a logically consistent way out of this, which is there would be no paradox if Alice's superposition were always decohering outside of a black hole, as if she was becoming entangled with any number of optimally sensitive observers that might or might not be hiding behind the event horizon. Right? That's at least a logically consistent way out, that you could guarantee that Alice, in the presence of the black hole, doesn't gain any information about what's going on inside. And this is a very different conclusion than you would expect outside of the cold, dead star. So hopefully now I haven't convinced you that this is necessarily true, but at least seems to be a logically consistent way out, and it's hard to imagine what else might happen to rescue causality and complementarity. Now, okay, you can actually compute the decoherence of Alice in this space-time, and as the thought experiment would suggest, there really is an unavoidable flux of soft entangling gravitons into the black hole that you can compute on the horizon. And those are not present in the neutron star case. And so there is an extra decoherence of Alice in the exterior, as you'd expect just from this causal consistency argument. Now, that's the subject of a number of preceding papers, so I'm not going to go into in great depth the derivation of that effect, but I'll just state briefly the outcome of those computations. So, due to this unavoidable emission of gravitons into the horizon, any superposed body outside a black hole will decohere after this time, this kind of characteristic coherence time, where this big capital D is the distance of Alice from the black hole, capital M is the black hole mass, and then the little m and little d characterize the size of Alice's mass superposition. And this is a very weak effect if you plug in numbers. But it is a universal source of decoherence because you can't shield gravitational fields. For a charged particle, you could run the exact same thought experiment for an electromagnetically charged particle, and as you might expect, the electromagnetic field, the Coulomb field, also goes into superposition, and you get a stronger effect in addition to the gravitational one. This is the way it scales now, with the charge replacing the mass and the dipole moment of the superposition replacing the quadrupole moment of the superposition in the denominator. And there's an analogous effect, as should be intuitive just from the causal consistency arguments I gave didn't depend in particular on the fact that it was a black hole horizon. There's a directly analogous effect that we find outside of the de Sitter horizon. So in a cosmological space-time, you also get this universal gravitational decoherence that is, again, very weak, and some electromagnetic analog of it too. Okay. So far in describing this, we've relied on the presence of the horizon to reason about the phenomenon. We've been doing these kind of global analysis of what must be true from causality. And this begs the question, everything we've been doing has either been in the context of perturbative quantum gravity, or in the case of the electromagnetic an analog, it's quantum field theory on curved spacetime, these are local theories. So there should be a local explanation of what's going on. In other words, you could ask, what would Alice blame for her decoherence if she knew nothing except what was going on in her laboratory? There should be a perfectly reasonable local explanation from her point of view. And this is a little bit confusing. Part of the reason the question is worth asking is because the metric in her laboratory is the same as it would be outside of the cold, dead star. So it's, you know, not just some effect of the metric or the local space-time curvature that can be blamed for the difference. So what is the local explanation? Why would Alice what would Alice attribute her decoherence in the black hole case that would be so different from just sitting outside of the star? Well, so to get a handle on this, it's useful to note that this number of entangling gravitons that I computed can be computed on the horizon, as was done before, but it can also be computed as it's equal to the variance of the local metric in Alice's laboratory, just smeared into the world line of her superposition. So you can interpret this number of soft gravitons as being the result, in this precise sense, of the vacuum fluctuations of the metric in Alice's lab. And if you analyze the power spectrum of those vacuum fluctuations, you find that there's, outside of a black hole, there's a extremely low energy quadrupole fluctuations of the metric in the vacuum that are not present in the quantized metric outside of a cold dead star. So in effect, a black hole kind of rumbles, or it emits these extremely low frequency quadrupole fluctuations, which do not make it out to infinity. They ultimately are reflected off of the angular momentum barrier, but they extend extremely far out into the space-time, far beyond the Schwarzschild radius, before being ultimately reflected back into the black hole. And these soft vacuum fluctuations of the metric locally in Alice's lab give rise to a stimulated emission of further radiation produced by Alice's superposition that falls into the black hole. So this is the kind of local effect, the local description of why Alice is decohering. And this raises a kind of natural question, which is, if could a material body be engineered to produce a similar vacuum in its exterior? Could I mock up the effects on Alice's superposition by replacing the black hole? We saw that the cold dead star wouldn't do it, but perhaps some other material body could give rise to a similar phenomenon.
Daine,
well, okay. Yes.
Is it so if I may ask
Please.
a question, maybe you come back to this
please.
point, but very interesting. So I was wondering, as you are explaining the importance of the vacuum fluctuations, making here a distinction between the two otherwise locally identical metrics, in particular the black hole case compared to the neutron star. So I guess that means that which vacuum state you are considering is, of course, important. In particular, I guess I would naively guess that maybe if you were considering that not so physical, but Bowler vacuum outside the black hole, maybe you recover something similar to the neutron star case.
That's a good question. So yeah, we analyzed the Bowler vacuum as well. The Bowler vacuum has as you say, it's not so physical because it essentially has a kind of firewall on the horizon. Mm-hmm. And actually, that was an interesting. I was fully expecting the Bowler vacuum to be identical, in essentially identical to the vacuum outside of the neutral star, but it actually isn't. It's not. It has some vacuum fluctuations all the way down to zero frequency, because you still have the kind of exponential redshift all the way to the horizon. Mm-hmm. But they're not nearly as severe. So what you get, instead of a exponential decay of off-diagonal elements of Alice's density matrix, you just get a power law decay.
I see.
So but you still get an effect. It's just much weaker. Whereas in the neutral star case, the effect just can be, decoherence can be made arbitrarily small. So yeah, it's actually the one of the kind of surprising to me conclusions was that the Bowler vacuum is not really suitable as a proxy for the vacuum outside of a star if you're concerned with the low frequency behavior of the Bowler vacuum or of the star vacuum.
And that, just to
Otherwise,
be
it's pretty good.
clear, you could have a neutron, well, not really a true physical neutron star, but Duncan experiment. So some neutron star was as close, but barely outside the Schwarzschild radius, and you would still get there, not even this power law decay, if I
Yeah,
am correct.
yeah, that's right. Yeah. Yeah, basically, as soon as the surface of the neutron star enters your past light cone, you would stop seeing you would no longer see any low frequency contribution.
I see. I see. Thank you.
Yeah. And I should say this is an expansion around low frequency. So what this is saying is that this is not the full power spectrum. This is saying that at low frequencies, the power spectrum approaches a constant, a non-zero constant. So there's like a plateau at low frequencies of fluctuations all the way down to zero frequency. Okay, so the next thing you could ask is that maybe I just add thermal fluctuations. A black hole is a thermal body, a dead star is not a thermal body. But actually, if you just do a thermal state in the space-time of a star, you also don't get this arbitrarily low energy vacuum fluctuations of the metric. So it's not just that. But you could try to imagine a better matter model, maybe by saying, well, the one thing I didn't do is I didn't model any excitable internal degrees of freedom of the body. I mean, that's why I've been talking about this cold dead star that has frozen out all the degrees of freedom, and everything Alice is doing is too adiabatic to excite those degrees of freedom. It is possible to develop a matter model with internal degrees of freedom, as Biggs and Maldacena showed, that mimics the effect. In the electromagnetic case, it's actually pretty easy to construct a model like that. You can just a chunk of hot aluminum can mimic the decoherence effect due to an electromagnetic or on an electromagnetic superposition outside a black hole. But the gravitational case, it's more interesting in that to mimic a black hole decoherence effect, you'd need an ordinary body with extraordinary properties of matter. Certainly not the standard model matter that fell in to form the black hole or anything like that. You need this kind of incredibly high shear viscosity. I think there's examples in, kind of more exotic kind of realizations of matter, like involving V-branes and whatever, that do exhibit some of these properties, but certainly it's not matter from the world as we know it with the standard model. So in principle, you can mock it up, but actually gravity is quite special in practice. Okay. The interior, so this whole story is kind of suggestive of kind of degrees of freedom of the black hole. I mean, even the fact that the black hole gives rise to this power spectrum of fluctuations outside, it's very suggestive of some kind of degrees of freedom in the interior. Of course, a classical black hole has no degrees of freedom whatsoever. So that's, and even semi-classically, this is just a suggestive picture. But we can get closer we can look at that, we can kind of get a better feel for this analogy with a body with degrees of freedom from the original Gedanken experiment, which involved this interior observer, Bob, which is some degree of freedom that we've stuck inside the black hole. And in fact, all this analysis I've just given you has been in terms of stuff on the outside of the black hole, but the original Gedanken experiment had to do with decoherence due to entanglement with an observer in the inside. So it should be possible to rephrase everything quantitatively in terms of the information available to an interior observer performing an optimal measurement or becoming entangled with the Newtonian fields from the outside. And that's what I'll show now, is that it is possible to reframe all of this from kind of an interior observer or interior degrees of freedom point of view. So operationally, suppose that there's some experimenter, Bob, trapped in the black hole. It's not Bob Wald. I don't want Bob to be trapped in the black hole. And also, this needs to be an extremely skilled experimenter in this Gedanken experiment. So, what's the probability, you could ask, that so we're doing the same experiment as before. Alice has made a spatial superposition of a body, massive body. There's a superposed Newtonian field that extends into the interior. What's the probability that by performing one optimal measurement of the superposed metric, that Bob can learn with certainty which position Alice's superposition is in? So this is what's called an unambiguous state discrimination task. And the answer is given in terms of the fidelity of the fidelity between the square root of the fidelity between the two states that reach Bob. So the two superposed states of the interior metric. And you can, what I'm going to show is that actually this operational notion of distinguishability in terms of an unambiguous state discrimination task is the one that's relevant to asking questions about decoherence outside of black holes, but from the point of view of the inside. So in order to do this, I'm going to want to model, I'll need to take a technical detour. So I'm going to model the black hole as a quantum channel acting on Alice. So a quantum channel is just a completely general description of a quantum experiment. And Alice is being acted on by the black hole channel. And then I'm going to give notions of decoherence and information. So decoherence of Alice and information available to Bob in this one-shot unambiguous state discrimination sense that are phrased in terms of the channel acting on Alice and a complementary channel which brings the information to Bob. So the complementary channel I'll denote with NC. C just stands for the complement, and that's going to be the effect of the decoherence on Bob in the interior. So what you can do is you can characterize the information available to Alice by the kind of, well, you can give a notion of the information available to Alice by asking what's the difference between, the information available to Bob, excuse me, in the sense of unambiguous state discrimination, so as measured by the fidelity, by asking what's the difference between the output of the state sourced by Alice, what's the difference between the state sourced by Alice and some uncorrelated state. If you can't tell the difference, then there's very little information going to Bob. But if they're highly distinguishable, then you can learn a lot about Alice. And that's precisely the notion that this I of NC captures. It just captures what is the probability that Bob can unambiguously discriminate between the state produced by Alice and some totally uncorrelated state. Okay, so that's a notion of information available to Bob by the complementary channel that's taking information from the outside and ferrying it into Bob. There's another notion, which is just the decoherence of Alice. N is the channel acting on Alice, and you can look at what is the what's the kind of unavoidable decoherence of Alice. So the way I quantify that is you say allow Alice to do an optimal recovery channel on her own system after the black hole has acted. That's this R. This R is an optimal recovery channel. And then see how different the channel is after this optimal recovery. How different is the net channel from the do nothing channel, the identity? If the identity channel would completely preserve her coherence, and now I'm going to let her do a recovery channel and see how close she can get to full recovery. And in the case of Alice's experiment, this more generalized notion recovers the kind of standard notion of decoherence as kind of 1 minus the off-diagonal elements of Alice's reduced density matrix in the specific case that we were analyzing before. So this is a kind of a suitable generalization of decoherence to the kind of arbitrary effects of a black hole, or just the arbitrary effects of any channel, really. So in the case that we're considering, it turns out that the probability that Bob learns in this sense of he can do an optimal measurement and gain certainty in one shot about what's going on outside precisely balances with the decoherence of Alice on the outside. And that turns out that's actually a special case of a general theorem that we prove using a result, a very useful result of Daine et al. One can show that these two operationally defined notions, this kind of information available to Bob in this one-shot discrimination sense, is actually precisely equal to the complementary notion of decoherence. And so the complete decoherence that eventually arises outside of a black hole implies a maximal entanglement with the complementary system, as if it were performing an optimal unambiguous state discrimination task on Alice. And as if Bob were realizing precisely the optimal experiment that he could do on the interior to try to learn what state Alice is producing. And this equality, between the information of the complementary channel and the decoherence of the original channel just holds for arbitrary channels. But here I've given it a nice, an interpretation in the context of black hole physics. And in fact, more specific to black holes, you can show that a black hole satisfies a sort of second law for decoherence. That if you consider the sequence of channels corresponding to Alice taking a longer and longer, waiting longer and longer in her experiment outside, the decoherence outside for a black hole, this is now not a general property of systems. Normally I can do things so to recover some coherence, but a black hole is in a sense optimally decohering, in that the decoherence due to a black hole is a strictly non-decreasing function outside of the black hole. And also correspondingly, just by what we've just seen, the amount of information available to an interior observer performing an unambiguous state discrimination task, of course, then also is a strictly non-decreasing function as you give him access to more and more of the full interior and allowing him to perform his experiment. So, this is kind of in this sense, you can view a black hole as performing an optimal and unambiguous state discrimination task on everything in its exterior. Good. Yeah. Okay. So we've kind of introduced this idea. I think I'm nearly done. That's good. So we've introduced this idea of Bob, performing his experiment in the interior and quantifying, how much, which path information he can get in the interior. And we've, introduced this idea that, I just told you that amount should increase as a function of time available to Bob. So let me be a little more concrete about what I mean by that. If I draw this, I take this horizon cut, and then I consider this, null hypersurface extending through the horizon cut. I can kind of, this is a convenient way of defining a kind of notion of time that makes sense for both Bob and Alice. So as I advance this cut, which I'll denote by the affine time VC, V cut, as I advance the cut, I'm kind of giving Bob access to more and more of the interior, because I'm going to restrict him to doing a measurement behind the cut. And I'm also considering the decoherence of Alice at later and later times, right? So this is, this is what I mean when I say that I'm kind of considering the finite, at finite times, how decoherent is Alice and how much information available to Bob, and basically restricting Alice and Bob to past of this dashed line here. And you can ask, what's the probability, as I was just saying, that Bob learns the distinction between the states restricted to the past of that dashed line in his region. And I've just given you some kind of general theorems about that distinguishability, but it would be really nice if we could actually compute it, compute a number for this distinguishability probability. And so in generality, this probability is bounded by the fidelity, and in the case of, in general, there's different notions of fidelity around. One is the Ullmann fidelity, one is the Holevo fidelity, and for the remainder of this talk, I'm going to focus on the Holevo fidelity, which satisfies many of the desirable properties as far as bounding Bob's state discrimination probability. Of course, in the paper, we'll also give the formula for the Ullmann fidelity, but this is more useful. So if you want to do this practical calculation, like what really is Bob's probability for distinguishing these states, you run into a problem, which is just a technical problem, which is that the states sourced by Alice don't vanish on the cut. And this is there's just a technical issue of trying to compute anything in quantum information theory for fields, which goes by the name of Tomita-Takesaki theory. There's just this kind of ultraviolet issue of when you cut through a field configuration that doesn't vanish on the cut, it makes things hard to compute. And that's something that's been pointed out. It's been long known, and it's especially been pointed out in a paper by Cassini et al. In 2019, where they call that the hard case, as opposed to the easy case, where the field configuration does vanish at the cut that you're trying to analyze the distinguishability on. So is this insurmountable? Well, I guess I wouldn't have this section of the talk if it were insurmountable. The answer to this technical challenge comes from an unexpected place, which is there's an asymptotic or a so-called large gauge symmetry on the horizon that allows you to transform field configurations by an overall time-independent shift on the horizon. That's a fact about these massless gauge theories, and it's these have been well understood at null infinity and also arise on a black hole horizon, these symmetries. So we're going to use that symmetry to basically transform the hard case into the easy case, as you can see here. I take something that doesn't vanish and I can do a time-independent shift on the horizon, and I get something that does vanish at the cut I'm trying to consider. Now, there's a problem with this, however, which is that in order to do this, the ordinary Hilbert space of quantum field theory that we usually consider, the ordinary kind of Fock space, doesn't allow for field configurations that are kind of non-compact on the horizon or at null infinity. They just doesn't allow for non-compact field configurations. But those are precisely the kind of configurations that we get when we do this kind of asymptotic symmetry analysis. Okay, what we do, and I am building up to something, but I realize this is a bit of a technical detour, is you can extend the algebra of observables on the horizon to include the deep infrared modes that include field configurations that do not decay asymptotically in time. Those are completely physical modes. In fact, those are precisely the modes that correspond to things like the memory effect. Those are literally responsible for the memory effect at scry, at null infinity, the gravitational memory effect. And there's an exactly analogous mode on a black hole horizon, or a bunch of modes, which are very physical, but which are just not allowed in the standard Hilbert space that we consider. And so you can just enlarge the algebra of observables on the horizon to include these physical modes. And you find that there's a unique extension of the Hilbert space. And in that unique extension, you can ask these questions about the finite time distinguishability of states, even if they don't vanish. Because in that enlarged Hilbert space, you can shift things around in a way that changes their, by time independent shifts, that changes their support properties even out at infinity. And just heuristically, I'm not going to explain this formula except at a cartoon level. But this formula realizes precisely, this is a formula for the, essentially what's called the relative Tomita operator, which is just an operator that allows you to compute distinguishability between field configurations. And what we were able to produce with this is a new formula for the general formula for the relative Tomita operator, the distinguishability operator between any two coherent states. And you get this by all the operator does is it does an asymptotic symmetry transformation to take the hard case and make it into the easy case so that you can split it. Then it just applies a well-known formula for the Tomita operator in the easy case, and then it transforms you back to the hard case. And then once you've got this ansatz for how it should look, you can just check that this operator satisfies the defining properties of the relative distinguishability or operator, or the relative Tomita operator, and it does. So once you've written this operator down and checked, it is the right object. And intriguingly, this information theoretic object has appearing within it things like the memory charge, associated with the gravitational memory effect at null infinity. Now here, the horizon memory effect on the horizon. These physical quantities appear in this information theoretic operator. And yeah, this is just for anyone who wanted to see exactly how everything is defined, but I don't plan on going to this unless someone wants me to come back to it. And so with that, you get a formula. You get a nice formula for the distinguishability of states according to Bob, to the past of the cut. And in this one-shot state discrimination sense. And that formula, is related to the kind of information according to the complementary channel that I told you satisfies a second law and is equal to the decoherence. But now we can give an explicit expression, and the explicit expression is closely related to all of those other more abstract things that we were computing. And it's just, in this case, for the Holevo fidelity, it's nothing more than kind of 1 minus the kind of magnitude of the field configuration on the horizon added to its CRT conjugate on the opposite side of the cut. So that's just a formula that you can then use. And I don't think staring at this formula is necessarily so illuminating without some more background explanation. But this is just to say that you have an explicit formula, you can go forth and compute distinguishability. And if you feel like jumping into a black hole at some point in your life, you can compute what you should expect for distinguishing states inside it. Okay. Yeah. And okay, this is just, I'm just pointing out, I think I can skip this discussion here. Okay, so we've developed a quantum information theory for soft radiation in this whole process. We did it because we were interested in a finite time question of how distinguishable are states on the black hole interior, according to Bob, at finite times when we're restricting him to have access to a finite interior region. And in the process, we were kind of driven by this technical consideration of the hard and easy case to enlarge the algebra to include these deep infrared modes. So it's natural to ask then, what is the contribution of these deep infrared modes to other notions of distinguishability, like the relative entropy, for example? And one can compute exactly what the answer is. And the answer is that there is a contribution, and it's that the variation of the relative entropy, it's that the memory on the horizon, which corresponds to just the kind of net change between early and late times on the horizon, acts as a sort of a chemical potential for the relative entropy of the horizon. And you can find this by taking the variation of the relative entropy with respect to the kind of canonical conjugate of the memory, which turns out just to be the sum of the metric, on the cut and at and in the distant past, whereas the memory is the difference of the metric over that same interval. And you compute the variation. I realize there's a typo on this slide. It shouldn't be holding the canonical momentum fixed. It should be that this is a leading order. This is, if you take a variation where the time derivative of the field is the time derivative of the varied field is extremely small, then this formula pops out. So you're considering variations that are not strictly zero canonical momentum, but just extremely small canonical momentum of the variation. So sorry for that typo. Then you find this quantum information theoretic relation, which is, kind of interesting to note as an analogy that there's a possible thermodynamic analogy in which the memory could be thought of as a sort of a chemical potential for the black hole, at least when it comes to extremely soft variations. And in the ordinary Hilbert space that would be considered without soft stuff, the right hand of the side would just always be assumed to be zero. But in you know in a physical black hole, it's not zero. Generically, there should be these soft modes do exist in nature. Well, and especially at null infinity, the memory effect is expected to be observed at LISA and LIGO, and so I certainly don't expect this memory tensor at null infinity to be zero. And indeed, this exact analog of this formula holds at null infinity as well. Okay, I think that's basically all I have to say. The punchlines are a black hole will eventually decohere any superposition in its exterior, and that decoherence corresponds to this kind of a secular accumulation of this one-shot distinguishability information in the interior that continues as long as the black hole is around. The decoherence proceeds as if the black hole were full of optimally entangling degrees of freedom. And a full account requires that you have a treatment of the soft modes on the horizon. Semi-classically, everything I'm doing is semi-classical. Of course, there will be corrections one might expect there to be corrections when a significant fraction of the black hole mass has radiated away and the metric has changed a lot. So at the page time, you might expect corrections to emerge when you work non-perturbatively in G Newton. It's outside the scope of what I'm talking about. All corrections would be all suppressed in those small parameters. But these kind of hypothetical bobs or degrees of freedom are very useful as mathematical entities for deducing a black hole's properties. Like we are able to use the existence of these hypothetical interior degrees of freedom to deduce the existence of the decoherence effect itself. And I thought I would add a quote that I thought was kind of intriguing, which is, by analogy, there was a time when it was believed that quarks were mathematical entities, best thought of as, kind of pure idealizations for determining the properties of strong matter. And indeed, there's this quote, as for Gelman, he had very good reasons for initially insisting that quarks are mathematical entities only. I think that, the ... speaks for itself as far as our understanding of quarks in the present day with respect to them being mathematical entities. So I think that's an interesting point to leave us on. So I think I'll conclude there. Thank you very much.
Thank you, Daine, for this very interesting talk, and also despite the complexity of some of the subject, I think you gave a very, very nice and clear introduction and motivation, and a very sort of interesting, intriguing final thought at the end of your conclusions. So do we have questions from the audience? So, well, let's see if people come up with some of the questions. I think I have some general questions that maybe are more suitable for the later discussion. While we are waiting for some questions, I might ask, they are really small technical details, so I would prefer someone else to come up with other questions, but otherwise, while we wait, I might ask some of those. Okay, so let me then maybe start and see if others have additional questions. So one point, it's probably a very simple thing, but I was just trying to understand. When you relate, quite at the very, very beginning, already in the simple setup, when you relate the decoherence to this, basically, the loss of coherence is exponential of -1/2 the expectation value of the number of gravitons on the horizon yes. So I guess well, maybe I don't remember correctly, but again, the simple thing that comes to mind is that in some sense, when I compute this kind of thing, what I would get would be something that would be at the operator level very similar, but in some sense from coming from the overlap of the radiation state, the state of the gravitons you get for the two branches.
Yes,
I guess
precisely.
that
Yes.
that can be just, I suppose that that can just be re exactly what you wrote here. I guess the point is that one can see that that can be expressed as expectation value of the number of gravitons, I guess, emitted by either of the branches. That's what you meant here, or is it compact notation as well?
Yeah, so good. So the what is meant here is that so n is what I'm calling an entangling is the expected number of entangling gravitons. So what you find is that it's the what you get is the kind of the Klein-Gordon norm, the number of gravitons in the mode of h left minus h right.
Okay,
Uh,
then
yeah,
I
so it's that's what I'm calling entangling
okay,
gravitons. It's
okay.
it's
So
it's
that's
gravitons in the mode that distinguish between the two
I
coherent
see.
states.
Okay, so now it's clear. So that's what then
Yeah,
exactly. Mhm.
yeah,
Oh, now we have, so the audience now a good number of questions are, so we just started up and then, okay, so maybe we
good.
can start with, I guess maybe Max was the first one to raise his hand.
Sure. Hi, can you hear me well?
Yes, yes,
Okay, I'm just on a train at the moment. I'm sorry, so I hope my connection is stable. I would have a rather general question. Thank you very much for this very
yeah.
interesting talk. So there was recently some works that were based on your calculations and your works, considering the effect of some kind of quantumness of the horizon. For instance, by including some minimal length in space-time leading to some minimal area, and therefore, in that sense, behaving a bit like a filter, which would filter the soft radiation and not let it enter into the horizon anymore. And a bit, I would say, taking away the opportunity for Bob inside the horizon to get sufficient information to somehow know something about Alice's experiment. But of course, this depends
Hmm.
on the size of the quantum of area or of the minimal length. And I'm just curious, in the formalism you presented in the end,
Yeah.
which was focused on Bob's point of view, is this something which you can implement there pretty straightforward or pretty easily, and then also get some maybe some result depending on the size of the cut or of the area, so of the depending on how you implement it, maybe on the frequencies that can still enter the horizon or which are filtered out.
Yeah, that's very interesting. I I know the work you're talking about, and I think it's extremely interesting. I I would so my I think it'd be very interesting to ask what even happens to the interior description in a model of that kind. Um, because yeah, there is a the existence of the smooth interior. It seems to me is tightly, the existence of the interpretation as a, this global interpretation in which you have a space-time for the outside and the inside relies, well, it implies that you also get a, kind of, let's consider the electromagnetic case, you get a Gauss law, and I can consider kind of surfaces that, that Gauss law enforces that soft radiation uh, enters the interior. And that's just a consequence of, even just, you could even see it as a consequence of classical Maxwell fields on a curved space-time background. And from that point of view, the horizon is not particularly special. The Gauss law still carries through, and there's a need for this soft radiation in order to enforce the Gauss constraints. Um, it's that discussion at least raises the question in my mind of whether the picture of a smooth interior really makes sense in the presence of if there is a minimal length that in effect truncates these soft modes, or prevents these soft modes from passing beyond the horizon, because from a if there is a semi-classical description at some level, it would seem to be it's hard to imagine how the Gauss law would still hold in that semi-classical description if the soft radiation doesn't penetrate. So, I'm curious whether or not the how I certainly don't know enough to really have strong feelings either way, but I'm curious how the smooth horizon description, even as a coarse-grained or a low energy description, emerges in a picture like that. And I think it would be, that touches on your question. I think it would be extremely interesting to analyze.
Oh, yeah, definitely. Thank you so much.
Thank you. So the next question was Alessandro had a question.
Can you hear me? Yeah.
Yes.
We can hear you.
You talked about quantum information associated to soft modes penetrating the horizon. So,
yes.
My question is there a sense, a meaning, a way to understand the soft modes and as not adding energy to the black hole?
Yes.
So soft that they do not add energy to the black hole.
Yeah, the precise statement is that it is possible, for the soft modes, the energy can be arbitrarily small. So, for whatever process you want to consider, you can tune the process, make it more adiabatic, so that the soft modes are lower and lower and lower energy. And there will always be some epsilon of energy involved in any physical process, but it can be made arbitrarily small. So in effect, yes, you can contribute essentially zero to the black hole. Essentially zero energy being added to the black hole.
Even if after integrating over all frequencies, if the process is chosen in the right way, you can have an epsilon for energy, which can be as small as you want. This is the point. Okay. Thank you. Thank you also for the very nice talk. Okay.
Thank you.
Sorry, I was muted. I was just saying that thank you for the question, Alessandro, and you can go ahead.
Hello, can you hear me?
Yes.
Yes.
Thank you very much. Very enjoyable. You may have said this and I missed. So when you were describing the experiment from Alice's lab point of view, you were saying that you are not putting the low frequency gravitons in the Buller state.
That's right.
I missed which state you are putting them in.
Good. Yes. So you can take it to be it's the computation goes through the same way in either the Unruh state or the Hartle-Hawking states, because those two states are in the very low frequency limit. They approach the same low frequency spectrum. So it's the Unruh state outside the black hole, or the Hartle-Hawking state, if you like. They have the same low frequency behavior.
You'd expect that in the Unruh state there is flux out. In the Hartle-Hawking state there is flux out balanced by flux in. So naively you would expect that whatever a prediction you get with the Unruh state, you would get twice that prediction in the Hartle-Hawking state. What am I missing if I think this way?
I think what you might be missing, I guess, it's a subtle question. I think we missed it initially too, is that these low energy modes never they are fully reflected off of the angular momentum barrier. So if you look at null infinity, these low energy modes, future or past, these, in the Hartle-Hawking state or future in the Unruh state, these low energy modes never make it to null infinity. But they make it extremely far out. So if you look at the angular momentum barrier, this is something that was puzzling us for quite some time. We started to hone in on this stimulated emission picture as the local explanation. But the low energy radiation is supposed to be what's responsible for this simulated emission. But if you look at the spectrum at null infinity of radiation, it has no support at zero frequency. And so how can it be that Alice's lab, which can be very far from the black hole, has anything to do, can see any signature of this low energy radiation? And the answer is that if you look at the angular momentum barrier at very low L, you find that and very the very low frequency, the kind of effective potential barrier that these low frequency modes see decays incredibly slowly as a function of radius. It does so. It's a very gradually decaying potential barrier, and so the modes penetrate very deep, quantumly into the barrier before ultimately being reflected back, meaning that even at, I don't know, 100 M or, very large, extremely large distances from the black hole, there's still a stimulated emission due to these modes, which ultimately will just fall back into the horizon. And that's, I think, that's why Alice, doing her experiment, can all the stimulated emission also falls into the black hole, and none of it goes to scry. So that's why I think where the kind of, the remarks you gave, it sounds like I think would completely agree with for radiation coming in and leaving scry, but actually that's not relevant here. It's all the white hole modes that bounce back.
On which side of the angular momentum barrier do you take Alice's lab to be?
Well outside. But the point is that there's no clear outside for very low, for these low frequency modes. So, the kind of, if this is the angular momentum barrier, it kind of goes off like this, and off at 100, Alice is out here at 100 M or something. But the modes still penetrate rather deeply, although ultimately not reaching infinity.
Thank you very much.
Yeah.
Thank you, Yoma, for the interesting question. So do we have any further questions? Otherwise, we could also, I think, stop the recording. So we also still have a chance for those who maybe didn't dare to ask a question or to have some extended discussion after the recording. So maybe Navdeep, it's a good point then to stop the recording.